Hi, in this video, we are going to look at practice problems for number theory. So let's get started. Uh, the first one is this one. Show that for all primes p greater than 3, 24 divides p square minus 1. So pretty simple question. We have to prove that 24 divides p square minus 1. So now p square minus 1, if you think about it, can be written as p minus 1 and p plus 1. We have basically p minus 1 and p plus 1 are not primes. If you think of the three consecutive numbers p minus 1, p and p plus 1, these three consecutive numbers, one of them has to be divisible by 3, right? Any three consecutive numbers, one of them will be divisible by 3. And we know that 3 does not divide p. Why? Because p is a prime. So 3 does not divide p. So 3 must divide either this p minus 1 or 3 must divide p plus 1, right? So we automatically know that 3 divides p square minus 1 because it will divide one of these two factors, right? So now what we have to prove is basically 8 divides p square minus 1, because if we can prove this, then we already know 3 divides p square minus 1. So we get both 3 and 8 divide, so 24 divides p square minus 1, right? So in order to prove that 8 divides p square minus 1, think of p as a prime number. So p can be of the form of 4k plus 1 or 4k plus 3, correct? It obviously cannot be 4k or 4k plus 2 because that will mean that it is divisible by 2, which is not true because p is a prime. So p has these two forms, and in both the forms you can check. If you say p minus 1 and p plus 1, case 1, where p is equal to 4k plus 1, in that case this expression becomes 4k and 4k plus 2, which is clearly 8 times k and 2k plus 1. So therefore 8 divides p square minus 1, right? And in case 2, when p is 4k plus 3, again you can see that it will become 4k plus 2 and 4k plus 4. And again, that implies that you can take 4 common here and 2 common here. So 8 will divide p square minus 1. So in all the cases, 8 definitely divides p square minus 1, and we have already shown that 3 divides p square minus 1. So basically we get that 24 should divide p square minus 1. Pretty easy problem, but you need to learn how to recognize the proof method that you will use here, right? We prove divisibility by a composite number by trying to prove that it is divisible by its prime factors, right? Let's look at the next one. Given that n minus 4 is divisible by 5, list which of the following the following numbers: n square minus 1, n square minus 4, n square minus 16, n plus 4, and n power 4 minus 1 are also divisible by 5. Divisible by 5. Great. So we know that n minus 4 is divisible by 5. So n minus 4 should be 5k. So n should be something like 5k plus 4, right? So if n is 5k plus 4, you can actually now check all of these cases directly. There is no issue here. you can realize that n square minus 1 would be basically what? Uh, n is 4 mod 5, so n is congruent to 4 mod 5. So n square will be congruent to 1 mod 5. Think about it, n square is 16, which is 1 mod 5. N square minus 1 is 0 mod 5. So it is clearly divisible, right? Similarly, n square minus 4, if n square minus 1 is 0 mod 5, it will be minus 3 mod 5, which is basically 2 mod 5, right? N square minus 16 would be congruent to, this will be minus 15 mod 5, so it is also 0 mod 5. N plus 4, n is 4 mod 5, so n plus 4 will be 8 mod 5 or 3 mod 5. And finally, n power 4 minus 1 is congruent to n square minus 1 multiplied by n square plus 1. But n square minus 1 is divisible by 0. It is 0 mod 5. So whole thing is also 0 mod 5. So the numbers that are coming divisible by 5 are n square minus 1, n square minus 16, and n power 4 minus 1, right? And the way we did it was we used congruences and we calculated the values of each of these expressions. So again, a pretty simple problem. I just want you to understand how to use congruences. Let's look at the next one. This question 3 is, if the same number r is the remainder when each of the numbers 1059, 1417 and 2312 are divided by d, where d is an integer greater than 1, you have to find the value of d minus r. So a simple problem based on the division algorithm by Euclid. So we will say that all of these numbers 1059, 1417 and 2312 are all congruent to R mod D, right? So writing that in terms of Euclid's algorithm, you can say 1059 is equal to K1D plus R, 1417 is equal to K2D plus R, and 2312 is equal to K3D plus R. They give the same remainder R when divided by D. So now you can use these three equations to create, subtract them and remove R, right? So if you use these two, you will get K2 minus K1 times D is equal to 358. Then we can also get K3 minus K2. Like third and second, if you subtract, K3 minus K2D is equal to 895. And then you can get K3 minus K1. K3 minus K1 times D is equal to 1253, right? So if you try to think of the prime factorization of these, it is 2 times 179, and this is 5 times 179, and this is 7 times 179. You can just check that. So now what we know is that the common factor of all of these three expressions must be 179. So D must be 179. And once you know the value of D, you can easily find K2 minus K1, for example, here, right? K2 minus K1 is 2 and all, right? So once you know D, I need to find out D minus R, right? So what we can do is use the D value in this expression. So we'll say 1059 is equal to K1 times 179 plus R. And now multiply 179. If you think about it, 5 times 179 is 895. So 6 times 179 would be, add 180 to it. So 5, 900, and then 175. So 1074, right? So 1074 would have been 8 times, 6 times 179. So therefore, R should be equal to minus 15, right? This can be written as 6 times 179 minus 15. So R is minus 15, or you can write R as 164 also. Because R must be a positive number, we can write it as 164, because you will say 7 times 179 plus 164, right? If you want to keep your remainder as a positive number. So then D is this, R is this. So D minus R is simply 15. We are using Euclid's algorithm and prime factorization to figure out the common divisor. And after that, it is pretty straightforward, right? Okay, let's go to the next one. Question 4. Find the sum of all x. Find the sum of all x where 1 is less than x is less than or equal to 100, such that 7 divides x square plus 15x plus 1. Okay, so this is a problem where you need to figure out what are the quadratic residues mod 7, right? So basically what we want is x square plus 15x plus 1 should be 0 mod 7, right? So then we have to think about what happens to x square. What are the possible quadratic residues of x square mod 7? So let's do it on the side here. If x is 0 mod 7, x square is obviously 0. If x is 1 mod 7 throughout, x square is also 1. X is 2, x square is 4. X is 3, x square is 9, so that will become 2 mod 7. And then 4 will become same. X is equal to 4 will match, so x square will be again 16, so that is 2. And 5 will be the same as this. X is equal to 5 mod 7. You will get x square is equal to 4. And finally, x is equal to 6 mod 7. You get x square is equal to 1 mod 7, right? So these are the possible quadratic residues. So you realize that x square mod 7 will be congruent to either 0, 1, 2, or 4, right? So x square mod 7 is congruent to 0, 1, 2, or 4. And if now we do those specific cases individually. So case 1 is if x square is congruent to 0 mod 4, then obviously x is congruent to 0 mod 7. And then this will be also 0 mod 7, and in overall it will become 1 mod 7. So that case is eliminated. Now think about the case when x was 1 or x was 6 mod 7, right? In that case, x square is 1 mod 7. It will be 1 plus 15 times 1 or 6 plus 1, right? So it will be either 1 plus 15 plus 1, which is 17, which is 3 mod 7, which is a case that we don't have to worry about. Or it will be 15 times 60, which is 90 plus 1 plus 1. So it will overall become 1 mod 7, because 91 is divisible by 7. So this case is also cancelled because you're not getting overall expression is to be divisible by 7, right? Then you look at x is equal to 2 and x is equal to 5 together, right? If you do x is congruent to 2 mod 7, what happens? X square is congruent to 4 plus 1 plus 15 into 2, 30, and 30 will become basically 2 mod 7. So notice that it is becoming 7 or 0 mod 7, right? So definitely this works. This is correct. X is congruent to 2 mod 7 works. So let's check 5 as well. That will give us also 4 here and 75 here. 75 is basically another 5 mod 7, and this is 1. So that doesn't work. So that case doesn't work. Now we look at x is congruent to 3 mod 7. So x square will be 2. If x is congruent to 3 mod 7, x square is congruent to 2. And 15 into 3, 45 is congruent to 3 plus 1. That doesn't work. If 4, it was 4, then you get a 2 plus 60 plus 1, which is divisible. So again, what works is x is congruent to 4 mod 7. So we have found by doing all the casework which ones are quadratic residues and which quadratic residues will satisfy the condition that 7 divides x square plus 15x plus 1. And we have found that those must be either x is congruent to 2 mod 7 or x is congruent to 4 mod 7, right? Once you know that, you just have to find the sum of such numbers from 0 to 100, right? 1 to 100. So these numbers here start from 2 and go on till 2, 9, 16 till 100. The sum of these numbers, there are two, it is 7 into 0 plus 2, and here it is 7 into 14 plus 2. So there are 15 numbers here. The sum of these numbers will be 15 by 2, n by 2 into first term plus last term, because this is an AP with G, is common difference 7, right? So first term plus last term becomes 102. So 15 into 51 comes here. So that becomes basically 765. And what happens here? These numbers start from 4, 11, and so on, and you go up till 95, right? And there are 14 numbers here, 0 to 13. 7 into 0 plus 4 is 7 into 13 plus 4. So the sum of these numbers will be 14 by 2 and 99, and that will be basically 7 into 99, which will be 693. So the overall sum is 765 plus 693. The answer is 1458. Right? We have found all the numbers such that 7 divides x square plus 15x plus 1. Okay, let's look at the next one. Okay, so in this question, we have to find the units digit of 7 power 7 power 7. Find the units digit of 7 power 7 power 7. So whenever you have problems like this, you can start thinking about what is the pattern of the powers that you get when you raise 7, right? So 7 power 1 is 7, 7 power 2 is 49, 7 power 3 is 343, and then you get 7 power 4 is 2401. So, and after that 7 power 5 will have multiply this by 7, the last digit will be 7. So what you see is the pattern is 7, 9, 3, 1, and then again it repeats 7 and so on. This is the pattern of last digits of powers of 7, right? So now since you have to raise 7 to a very high power here, it would be good if you knew how many groups of 4 come in the exponents here, right? So what you need to do is find out 7 power, what is 7 power 7 mod 4, right? If we know what is 7 power 7 mod 4, then we'll be able to decide which of these cases is actually the situation, right? So we know that what we know here is that we know 7 power 4 is is giving a last digit of 1. So how do we calculate 7 power 7 mod 4? That is the question. Okay, so since we have to do it mod 4, let's think about it. 7 power 7 mod 4 will be congruent to 3 power 7 mod 4, right? Because 7 is congruent to 3 mod 4, correct? And once we get 3 power 7 mod 4, we can write that as 3 is congruent to minus 1 mod 4. So it is minus 1 power 7 mod 4, which is congruent to minus 1 mod 4, right? So minus 1 mod 4 is basically 3 mod 4. So what we have gotten is that 7 power 7 mod 4 is equal to 3 mod 4. So this overall expression is 7 power 3 mod 4. So this integer is basically 4k plus 3, right? So if it is 4k plus 3, this was 4k plus 1, this was 4k plus 2, this is 4k plus 3. That means the power of 7 here will fall under this category, and so the units digit is going to be 3, right? Because here the units digit was 3, it is falling under this category of powers, right? So we have figured out that 7 power something 3 mod 4 will always end with the digit 3, right? Okay, now let's look at another problem. Uh, what is the largest subset? What is the largest subset S of the set 1, 2, 3 till 50? What is the size of the largest subset? That is the question. What is the size of the largest subset of S, which is 1, 2, 3 till 50, such that no pair, no pair of distinct elements of S, no pair of distinct elements of S has a sum divisible by 7, has a sum divisible by 7. So we have to construct a subset of this set from 1 to 50 such that you can never pick two numbers from the subset which are summing up to 0 mod 7, right? So think about it. The subset S cannot consist of elements like 1 mod 7 and 6 mod 7 together, right? We can't consider both of these elements. Similarly, we can't have elements like 2 mod 7 and 5 mod 7. And we cannot have elements like 3 mod 7 and 4 mod 7. These types of elements cannot coexist because as soon as you take two elements here, one of this kind, one of this kind, the sum will add up to 0 mod 7, right? So one way to do this, think of these groupings: 1 mod 7, 6 mod 7, 2 mod 7, 5 mod 7, 3 mod 7, 4 mod 7. If you want to make the biggest possible set, what you should do is take one element from here, from this group, 1 mod 7, take all the elements from 1 mod 7 group, and take all the elements from one of these groups, 2 mod 7 or 3 mod 7, right? So basically, if you select all the possible elements 1 mod 7, all the possible elements 2 mod 7 and 3 mod 7 without selecting the 6 and the 5 and the 4, you will never get a pair that will add up to 0 mod 7, right? Also, you should also think of elements that are actually divisible by 7. 0 mod 7. You cannot pick two numbers like that. However, you can pick one number from that set, right? There will be 7 numbers there, 7 into 1, 7 into 2 till 7 into 7. There will be 7 numbers there. You can pick one of them. Why? Because this one of them doesn't make a pair such that it adds up to 0 mod 7 with any of these, right? So let's count how many elements are there which are of 1 mod 7 type in this set. Starts from 1, goes on till 50. So there will be 8 such elements. Elements of the type 2 mod 7 will be 7, and elements of the type 3 mod 7 will be 7. And then we can pick one number which is 0 mod 7. So the total comes out to be 8 plus 7 plus 7 plus 1, which is 23 elements. So you can make a subset of 23 elements containing from this set such that no two of the elements of this subset S will add up to 0 mod 7. How did we choose that? We selected all possible numbers from the congruence classes of 1 mod 7, 2 mod 7, 3 mod 7, and we chose one number from the 0 mod 7 class, right? And that helps us construct the appropriate subset. Okay, let's move on. This is the next one. Let f of x be equal to x square plus 3x plus 2, and let s be the set of integers from 0, 1, 2 till 25. Find the number of members small s of the set capital F such that f of s has remainder 0 when divided by 6. This is a similar problem to what we saw earlier. What we have to basically figure out is find the number of members which are divisible by 6 here, right? So what we can say is we want to find out when the 6 divide s square plus 3s plus 2, or s square plus 3s plus 2 should be congruent to 0 mod 6, right? The easiest way to do this is doing the casework here. So you can say that S could be basically 0 or 1 or 2 or 3 or 4 or 5 mod 6. And obviously S square will be 0, 1, 4, 9 becomes a 3, 16 becomes a 4, and 5 becomes a 1. So 0, 1, 3, 4. These are the possible quadratic residues for mod 6, right? These are the cases. So now s square plus 3s plus 2, you can just check the cases. It's pretty simple. Let's check the case when s is 1 mod 6. If s is 1 mod 6, s square is 1 mod 6, 3s is 3 mod 6, and there is a 2, so that becomes a 0 mod 6. So s is congruent to 1 mod 6 fits, right? Similarly, s is congruent to 0 mod 6 doesn't fit. 1 mod 6 fits. 2 mod 6, let's check. If s is 2 mod 6, then s square is basically 4. So 4 plus 6 plus 2, which is 12, which is also fitting. So 2 mod 6 also works. Similarly, you can check that s is 4 mod 6 and s is 5 mod 6 also work. In all of these cases, you will get that 6 divides the s square plus 3s plus 2 expression, right? So because of these 4 cases working, we just have to count how many elements of these types are present in the set 0 to 25, right? So you will realize that the total number of such elements is 17. You can do a direct count, or you can eliminate the cases of 0 mod 6 and 5 mod 6, because those are the only two cases of numbers which are not satisfying this relation, correct? A pretty easy idea once you know what we are doing in quadratic residues. The next one is this one. For any integer n, greater than 1, How many prime numbers? How many prime numbers are greater than n factorial plus 1 and less than n factorial plus n? Right. Now think about this. Uh, we have all since all the numbers from 2, 3, 4, etc. divide n factorial. So we know we can say for sure that n factorial is definitely even. So when you add n factorial plus 2, we know that 2 divides n factorial plus 2, right? Think about it. What I'm saying is n factorial itself was divisible by 2, 3, 4, and all of these numbers till n, right? So 2 divides n factorial. So obviously 2 should divide n factorial plus 2. Similarly, 3 divides n factorial. So that implies that 3 should divide n factorial plus 3. And 4 should divide n factorial plus 4. And similarly, we can say that n should divide n factorial plus n, right? You could also say n minus 1 should divide n factorial plus n minus 1, right? That is true. So these things just tell us that the numbers from n factorial plus 2, n factorial plus 3 till n factorial plus n minus 1, all of these numbers have divisors which are not just 1. So basically 2 divides this, 3 divides this, n minus 1 divides this. And that is true because we know that n factorial is divisible by all of these numbers. So this is just basic. So that shows that any of these numbers that are lying between this and this, all of these numbers are not prime, right? N factorial plus 2, n factorial plus 3, till n factorial plus n minus 1 are all not prime. So the answer for this question is simply 0. How many prime numbers are there? The answer is 0. Okay, let's look at the next problem. Find the last three digits of 9 power 105. So typically the question here is 9 power 105 mod of 1000. That is your question. So you can try doing it by modulo method, but the easier method here would be using binomial theorem because 9 can be written as 10 minus 1 power 105. And then you can just expand this and realize that this will become 10 power 105 minus 105c1 10 power 104 and so on till 105c 102 10 cube times minus 1 power 102. Why have I isolated terms till 10 cube? Because we have to check division by 1000 here. So all of these terms are anyway divisible by 1000. And then there are some extra terms plus 105c 103 10 square minus 1 power 103 and finally 105c 104 into 10 to minus 1 power 104 and the last term will be minus 1. So we know that the first of these terms are definitely divisible by 10 cube because their powers of 10 are bigger than 3 here, right? So let's focus our attention on these terms and calculating the value of these. So this becomes basically negative of 105 into 104 by 2 multiplied by 100 plus 105 into 10 minus 1, right? So this becomes basically 52, and you get, since you have 105 and 52, the product of this will be a multiple of 10, and you already have a 100 here. So this whole thing is multiple of 1000. You can calculate it and check, it will be a multiple of 1000. So that is going to be 0 mod 10 mod 1000. So we have to only worry about this, which becomes 1050 minus 1, which is 1049, which is basically 49 mod 1000. So the answer for this question, the last three digits will be 049, because you are getting 1049 here, right? The idea is that the number overall came out to be some 10 cube times some capital A plus 1049. So that becomes our answer for this particular problem. We have isolated the 10 cube by basically taking binomial theorem and collecting all the higher powers there. Let's look at this question now. Find the last two digits of 7 power 9999. So what we have to think about here is 7 power 9999 mod of 100. The remainder when it is divided by 100. So what we can say is 7 square is congruent to 49 mod 100, and 7 cube is congruent to 43 mod 100, because it was actually 343. So mod 100 is 43, and 7 power 4 is congruent to 1 mod 100, which is useful because 7 power 4 was 2401. Mod 100, that is simply 1. Now, because we know 7 power 4 is congruent to 1 mod 100, it makes our calculations here a little easier. We can say this is 7 power 4 into 2499. So power 2499 into 7 power 3 mod 100. And we know this is congruent to 1. So this becomes 7 power 3 mod 100, which is 343 mod 100, which is congruent to 43. Are you on? I hope everybody is understanding what we are doing here. So we have basically figured out the last two digits of this expression, right? This number. Let's look at the next one. The question is this: let x and y be integers such that 17 divides 2x plus 3y. We have to show that 17 also divides 9x plus 5y. So the typical process here is to try to get 9x plus 5y in terms of 2x plus 3y somehow, right? So how do we do that? We can write 9x plus 5y as 17x minus 8x and 17x minus 12x, right? 17x plus 17y minus 8x minus 12y. So this is 17 times x plus y minus, if you take a 4 common, you'll get a 2x plus 3y. So you have 9x plus 5y is equal to this, and now we know 17 divides 2x plus 3y. Since 17 divides 2x plus 3y, we know 17 divides this part of the expression, and anyway 17 divides the first part of the expression. So it follows immediately that 17 divides 9x plus 5y. How do you think of this split? You have to do some trial and error. You have to get, you can say 9x plus 5y is equal to some Lx plus my minus mu times 2x plus 3y, right? And hope that you can solve for mu and L and m by looking at these numbers. At least find one solution, right? It's basically guesswork, but once you do the guess, it's over, right? Okay. Now, let's look at this particular problem. Prove that if exactly one of x and y is a multiple of 5, is a multiple of 5, then we have to show that x power 4 plus 4 times y power 4 is not a multiple of 5. So first thing is, always think of this. This is a standard factorization. So you can write this as x power 4 plus 4 power y power 4 plus 4x square y square minus 4x square y square. So now you can write it as a difference of two squares. So this becomes x square plus 2y square whole square minus 2xy whole square. So that becomes x square plus 2xy plus 2y square and multiplied by x squared minus 2xy plus 2y square. And that becomes basically x plus y whole square plus y square multiplied by x minus y whole square plus y square. This is what is coming here, right? Now, we have to say that if one of x and y is a multiple of 5, then this thing is not a multiple of 5. So without loss of generality, let's assume x is a 0 mod 5 situation, right? One of them is a multiple of 5. So y can be what? Y can be 1, 2, 3, or 4 mod 5. Great. So if x is 0 mod 5 and y is 1, 2, 3, or 4 mod 5, then you should realize that x plus y will be 1 or 2 or 3 or 4 mod 5. And we can just do the calculations in all the cases. Case 1, x is congruent to 0, y is congruent to 1. In that case, what is coming here? X plus y is 1 square plus 1 square multiplied by 1 square plus 1 square. So that is congruent to basically coming out to be 4 mod 5. Right? Now what is case 2? X is congruent to 0 and y is congruent to 2. Again, you will get 0 plus 2. So 2 square 4 plus 4, 8. And this is 4 plus 4, 8 again. So you're getting 64, which is 4 mod 5. So actually, you will see that in all the cases, case 3 and case 4 as well, you are going to get 4 mod 5. So that completes our proof. It shows us that in all the cases, your expression x power 4 plus 4 times y power 4 will always be not divisible by 5. We will continue with more problems in the next session. We are going to do a lot of problems. This is a problem solving session. We'll also have theory classes in between for number theory. So stay tuned and keep watching and keep learning, and I'll see you next time.